So we'll take a look at some examples of counting techniques. And at the top here, I just put a little visual for you of the difference between permutations of objects and combinations of objects. So what we want to remember with permutations, when we arrange objects, there's positioning involved. So like first place, second place, third place. So by having positions, if we were to change the order, we would get a different outcome. So if the green was in first place, that's very different than red being in first place. All right, combinations, on the other hand, there is no positioning. You can just think of it as a collection, so a group or a set. So let's take a look at some examples. So number one, 80 athletes are running a race. A gold medal is to be given to the winner, a silver medal to the second place finisher, and a bronze medal to the third place finisher. Assume there are no ties. In how many possible ways can 3 medals be awarded to 80 athletes? So hopefully it's clear here, position matters because winning gold is definitely different than winning bronze. So a permutation here would apply. So capital P, permutation, and then 80 would be the total athletes to choose from. And we'll be positioning 3 people to put in places gold, silver, bronze. So I'm not going to actually write the numerical answer here. You have a graphing calculator that can do that part. We're going to focus on getting through the problems and how to know what method applies for counting. All right. I did not put another visual up here of the first technique we learned, which was the fundamental counting technique. And we'll be reviewing that here as well. But let's continue with number 2. A company that makes crayons is trying to decide which 5 colors to include in its promotional mini box of crayons. The company can choose the 5 mini box colors from its collection of 40 colors. All right, I want to point out that for both this one and the previous one, we were picking some colors, 5, from a total of 40 possible. In a similar way up top, we were picking 3 people to win medals, choosing from a group of 80 athletes. So we have that sort of setup of picking some people from a group or some colors from a set of colors. We can always try to think of combination or permutation. So in this case, with picking colors, we're really just looking at a collection of colors to include. So there's no discussion about ranking the colors or positioning the colors. They're just trying to pick their 5 colors that they'd like to put in their mini box. So that one you can think of as an ungrouped set, a collection. So if it doesn't say something about positioning or ranking, then it leads us towards collection or combination. So a collection, another way to think of it is a team of colors. So teams, there's no ordering. It's just an equal collection, like the 5 colors they would put in their box. All right, number 3. How many different committees of size 4 can be formed from a group of 12 people? All right, so a committee is similar to a team. So each member is equal. There's no positioning or ranking of them. Again, that's like a group of people here on a team together. So a committee, if no positions are mentioned like chair, co-chair, it is a group of equals. So from the 12, from the 12 people, we would be choosing 4 to serve on the committee. All right, as opposed to number 4, a club with 12 members, they're going to select a president, a vice president, a secretary, and a treasurer. No person can hold more than one office. So in this case, we are definitely talking about putting people in a position. So becoming president would be very different than becoming vice president. So the order of placement here is going to be taken into consideration when we count possibilities. So this would be a permutation from 12 people. We would be picking 4 people to put in those 4 positions. All right, and then we have to log on to a computer account, the user must type in a 3-letter password. In such a password, no letter may be repeated, and only lowercase letters of the alphabet may be used? How many passwords are possible? All right, so this is a pretty boring password, and we just kind of go with it here. So it's just 3 letters, and we can't repeat letters. So would positioning matter, or is your password just a group of letters? So I'm just going to return to my picture here. So if this were your password, red, blue, green, that would be a different password than, say, green, blue, red. So changing the order of the letters, of course, would create a different password. So that would be a permutation. The arrangement there and different orders will give you a different password. So since it's only lowercase letters of the alphabet, we would have 26 letters of the alphabet to choose from, and we're picking 3 to put in those positions of the first letter, the second letter, and the third letter of our password. All right, number 6. A menu has 10, oops, sorry about that. A menu has 10, there we go. A menu has 10 appetizers. You're going to order 3 different appetizers to serve at a party you are throwing. How many different groups of 3 appetizer orders are possible? All right, so I can think of this one again sort of as a team of appetizers, a collection of appetizers. We're not ranking them or sorting them, positioning them in any way. We're just trying to figure out what are we going to order for our party. So again, it's sort of like this situation, whatever those 3 appetizers are, we'll just pick them and have them delivered to our house. So combination are all the ways that we could choose from 10 appetizers, the ways we could pick 3 of those. All right, versus number 7, a menu has 4 desserts, and we'd like to know how many ways there are to rank the desserts. So now we're definitely talking about positioning mattering. So for example, if cheesecake is your first favorite, that would be a different outcome than cheesecake being your second favorite. So we would be positioning our choices in these locations. So permutation involves ranking or positioning. And we've got 4 desserts. And in this case, we're going to rank all 4 of them. All right, now, those last 2 examples, I'm going to highlight some things. So for number 6, we were choosing 3 appetizers from a possible group of 10. And number 7, we were choosing to rank 4 desserts from a group of 4. So I want to look at how 8 is worded. So for 8, it says for house painting project, there are 3 colors available for walls, 4 colors available for an accent wall, and 2 colors available for a trim. How many ways are there to select a color scheme? All right, so this is not going to be the situation like the 2 above, where we're picking one group from another group, one group from another group. This one is making a sequence of choices. So our sequence of choices will be picking our wall color, our accent wall color, and our trim color. So this returns us to the fundamental counting principle that we started this section with. So the fundamental counting principle talked about keeping track of the choices we need to make as we go through picking our colors in this case. So we keep track of the number of possibilities for each decision. So for wall color, we had 3 choices. And then the fundamental counting principle says multiply by the possible choices for your next choice. So we choose our accent color, and they said 4 colors were available. And then we went on to pick our trim color, and they said that we had 2 colors available. So the fundamental counting principle says multiply. I'll put the value here, multiply. So there would be 24 different color schemes we could create with these decisions, these colors that are available. So 24 different color schemes. Okay, number 9. In how many ways can a researcher select 6 rats from 27 rats and assign each of them to a different test? So the key here is if they're assigning them to a different test, I'm just going to return to my picture. It's sort of like this scenario again. If the red rat does task 1 and the blue rat does task 2, that would be different than putting the blue rat first and the red rat second, because they're doing different things. So they really are being positioned into these tests where each one is different. So changing the order would put a rat in a different position, a different test that they would be trying to complete. So this is another example of, we would position the rats, so 27 of them to choose from, and we would select 6 to position in one of the 6 tests that the different tests that the rats would be performing. All right, and then number 10. From a group of 25 veterinarians, 5 will be selected to join a team that will study best practices in their community. How many different possible teams could be formed? So we're back to this idea of a team, which is just a collection of people. There's no ranking. It's just 5 equal people sitting on a team, a committee together. So that's going to be our combination. So we'll have 25 veterinarians, and we'll be picking 5 of those to serve on this team. Okay. So we'll be using our calculator to find the values of the combinations and the permutations, and I'll go back and include those values now. Okay, so just going back to the top, you'll be using your graphing calculator to enter these. So if you did want to check the numerical answers, I'm sure that you'll be fine here since you have your calculator. But that first one with the athletes, there would be 492,960 ways that we could award medals. So I'm just adding the English here so you know what we're talking about. That's a lot of different ways, but it's that many ways to award these 3 medals, where we're picking 3 people out of the 80 athletes that competed. And then with our box of crayons, we're picking 5 colors to put in our promotional mini box. And this is also going to sound like a lot of choices. So 658,008 different choices possible for the colors that we put in our mini box. So I'll just say again here with the English here, there are this many mini boxes possible. So the company is going to have to pick one of those 658,008 ways, one of those possibilities to put just 5 of their colors out of their 40 in the box. All right, and then the committee question, this will come out to be 495 ways that they could form a 4-person committee. And then the permutation for picking president, vice president, secretary, and treasurer will be 11,880 slates of officers possible. I'm just going to say ways that they could pick their officers for their club. And then with our password, even just 3 letters and just lowercase letters of the alphabet, that's still going to be quite a few passwords possible, 15,600 possible passwords. So with more of our real world passwords these days, obviously there's going to be a lot more than that, but that's our very simple example. And then for number 6, with our menu, if we're going to have 3 appetizers chosen for our party, and we can choose from 10, that's going to give us 120 ways that we could order a group of 3 appetizers to serve. Still a lot of choices. And then if we're ranking our desserts, there are going to be 24 ways to rank 4 desserts. And we'd be ranking all 4, like our first best, second best, third best, fourth best. All right, and then we got the fundamental counting principle. And then we got to our rats that we're doing different tasks. Now, this is going to seem like a very large number, but it turns out to be 213,127,200 ways to assign the tasks. So sometimes it doesn't seem intuitively correct. These number of ways can get incredibly long, but we actually could make a list of all these possibilities, but clearly we would not make a list with this many entries. And then finally, 25 veterinarians, and we're going to pick 5 to be on a team. And so there would be 53,130 different teams that are possible. All right, so we end this saying the whole point was to figure out how many ways there are to do something. And for these, we're just getting these numerical answers. But we started this whole process with the fundamental counting principle. I'm just sliding back here. So as we first learned the fundamental counting principle, we did take a moment to actually list the possible outcomes, not just say there were 6 outcomes. But we then went to different techniques to learn how to count possibilities, 6, without going through necessarily the process of trying to list them. All right, and that ends our discussion of counting rules.